All right, so now we'll have a mock lecture by Professor Mark Bowen, who's a major in mathematical sciences. So Professor Bowen, please.
Thank you. Thank you. So good afternoon. Nice to see some smiley faces. So as I said, my name's Mark Bowen. This is my email address. If anybody has any questions that you wish to ask about the program or anything I'm going to talk about today, feel free to email me. The professors in the international program are kind of very informal, so we usually go by our first name. So if you want to call me Mark, that's perfectly okay. So if you have any questions, feel free to ask. So today, the topic I'm going to be talking about is mathematics in action, subtitled Brief Tour for Infinity Limits and Differential Calculus. So what I decided to do with this was to give you guys like a kind of an overview of some of the topics that you would come across in an introductory calculus class at Waseda. So for example, if you guys have been studying a lot of calculus already, then a lot of this will actually probably be very common to you and you already know it. In which case then that's great because it means that if you come to Waseda, you'll feel very comfortable in the first year with the level of mathematics. At the same time, I'm also aware that sometimes people haven't studied any calculus, and in the classes that we have of maybe 60, 70 students coming in, we have a range of people who have studied maybe 2 years of AP calculus, and some people have done no calculus whatsoever. So at the same time, I didn't want to be too technical. And so what I want to do today in terms of what we talk about mathematics in action is actually talk about how it's actually used and how we actually understand the concepts rather than the actual fine print details of the technical kind of calculations that we undertake. So I'm going to try and skip away from that mostly and just kind of give broad strokes of different areas. So in particular, we're going to look at infinity and problems that arise due to infinity, and how we get around those due to limits. And we'll look at two particular examples, both of which come from, say, the introductory calculus class, but one of which is kind of not really differential calculus, and the other one is actually focused in the area of differential calculus, and I'll give a quick background to that too. So the first thing that we're going to note here is infinity. So this is the traditional symbol for infinity down here. And the first thing we have to think about is that we can't regard infinity as being a number, right? In mathematics, as far as we're concerned, we're going to have to regard infinity as a concept, right? There is nothing we can actually say as being, this is the infinite number, this is the largest possible number, because as soon as you say that, someone else just has to say, well, that number plus 1, right? So you can't define infinity. Likewise, you can't define an infinitesimally small number. That's also impossible because someone just has to say, well, take that number and divide by 2, and it's even smaller. So when it comes to infinity, there are difficulties because we can't give it a numerical value. And so we're going to have to consider it as being a concept in the calculations that we talk about. And so as I say, I'm going to say mostly broad strokes, and rather than getting into the real details, I'm just going to give an overview of the main concepts. So the first thing we'll talk about is a limit, right? And in essence, a limit is described by these 3 pictures, which you can think about as being at different times. So what we have basically is a lazy cat sitting on the right-hand side of this red line, waiting for the mouse. Right? And as time progresses, the mouse gets closer and closer and closer to the cat. Because the cat is very lazy, unless the mouse actually reaches this red line here, it's not going to do anything. It's just going to sit there. And so the mouse can keep getting closer and closer and closer. And as long as it doesn't reach that red line, then it's perfectly safe. Right? And so this is the process of what we mean by limit, that we can approach and get closer and closer and closer to a particular value or particular point, but we never actually get to that point, right? We always remain safe. The mouse never gets eaten by the cat. It never reaches that red line, right? So in essence, when we're talking about a limit, we say that we're getting increasingly close to the limit point, getting closer and closer and closer, the limit point here being this red line, but we never ever get there. So the mouse never gets eaten, and the mouse moving towards the cat is exactly the same as if we had a mouse moving towards an elephant or a person or a house or anything else. It doesn't matter what's actually here because the mouse never actually gets there. It just gets arbitrarily close. And that's the essence of a limit. So just introduce a little bit of mathematical notation, right? Limits we usually denote by the shorthand notation lim. Right? And then we have to define both the limit point, the variable that we're moving towards, and also the function that we're interested in. So maybe in this case, we're looking at how the mouse gets closer and closer towards the cat. That's the limit. So this is the variable approaching the limit value. And maybe we're interested in how scared the mouse is or how much courage it has as it approaches. Maybe we can measure that using connections to its brain or something like this. Okay, so this is just a shorthand notation for a limit process. Okay. But the essence, of course, is we can get as close as we like, but we never, ever get there. So the mouse will always remain safe and never get eaten by the cat. Okay, so now let's bring in another cat. So we're now going to have a situation where two cats are now playing with the mouse. The cats are going to start 10 meters apart. Say from here to here is a distance 10 meters. The mouse is between them. The mouse is going to start just in front of this left cat here. And the mouse is going to run, obviously, because it's a cat, right, this direction away from it. So it's going to run with a speed of 2 meters per second away from the cat on the left towards the cat on the right. Okay, so this is not a very clever mouse. If this was a clever mouse, you'd realize he lives in three-dimensional space and run off in a different direction. But this is not a very clever mouse, so he's just going to go backwards and forwards in one dimension. So the mouse will start running away from the first cat towards the second cat at 2 meters per second. And then when it meets the other cat, it's going to turn around and go the opposite way. Okay. And as the mouse is doing this, the cats are going to move towards each other at a speed of 1 meter per second. Okay. And what we'd like to know is, well, what is the path taken by the mouse, right? So at each time it meets a cat, where does it do so? So in the first process, the mouse is running away from the first cat and meets the other cat coming in this direction. And it meets at that location, we'll call it x1 at 20 over 3. So that's where the mouse first meets the cat from the right, coming from the right. And then it goes running back the opposite direction and meets the other cat, which is still coming from the left. And now it meets it at this location, 20 over 3 minus 20 over 9. Right. And this process then continues. It turns around again, goes back towards the right, meets the right-hand cat at 20 over 27, turns around again, runs the opposite direction, then runs back again, and so on, and so on, and so on. So we get this sequence of numbers, each time we're adding an extra bit, of the location of where the mouse meets the cat each time. And so after this is done n times, we end up with this finite sum, all the values up to and including this term here, where the minus 1 to the n plus 1 is just to give us the plus or minus sign. There's a factor of 20 in each case, and then 1 over 3 to the n. Right. And so, quick quiz. What happens to this value xn, right, as n gets very, 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 very large? You guys weren't expecting quiz, right? So what happens to the value xn as n gets very, very large? So we get this value to this value, this value. If we keep going, well, what happens to the value xn as n gets exceptionally large? And the hint here is think physically about the process more than mathematically. So what happens to xn as n gets very large? In the middle. So the idea is, well, if you think about it, the cats are coming in closer and closer and closer from the left and the right. The mouse is running backwards and forwards. Right? Where does this value actually end up? Well, as we get very large values, it must get closer and closer to the value 5, right? Halfway between, because that's where the cats are going to meet, right? So, thank you. So xn gets closer and closer to the value 5, where the mouse is eventually going to get caught by the cats. Right? Does that kind of make physical sense? Right, okay, so we have a physical reason why xn would be 5 for very large values of n. Right? So again, this is where infinity is coming into the problem, right? Getting larger and larger and larger values of n, but we can't actually get to infinity. We just keep getting larger and larger. Right. So what we'd like to do is to replace that finite sum by an infinite sum, or what we call an infinite series, which is these values going out to basically infinity, and then just to keep going and going and going and going. And we'd like that to equal the value 5. Right? And this leads us to a conceptual problem, because what we're effectively doing, if you think about the process, is we're actually adding up conceptually an infinite collection of numbers and getting a finite answer. And getting a finite answer is what we basically call convergence. Yeah. And so that might seem a bit peculiar, that we can add up an infinite collection of numbers and get a finite answer. And you may well say, well, yeah, but this is kind of a trick, right? Because some of these numbers are negative, some of these are positive, so the bits you add on, the other bits get subtracted off, and therefore it's perfectly okay. And that's one of the reasons this one does work, and that's true, but we have to be aware there's a bigger structure here. And in fact, actually, if I take some infinite series of just positive terms, then those things can also converge. So it isn't just the fact there's pluses and minuses going on here, there has to be something else going on behind the scenes. So just to give you a couple of examples of that, so here's one, quarter plus a 16 plus 1 over 64 plus 1 over 256 plus dot, 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 out to infinity, I claim is equal to a third. And there's a very nice geometric kind of picture of this. So this is a square of 1 by 1. And so the colored block here is a quarter. So that's the first entry. And then this block here has area 1 over 16. This block here, area 1 over 256, and so on, and so on, and so on. And what we notice is, well, in each case, it's a third of the region. So these numbers must add up to be 1 over 3 from a geometrical argument. Right? So this is a sequence of positive numbers that add up to give us a finite value. And it's not even a large finite value, it's just a third, right? 0.333333. Right? Another example of this. No, guys, graphical example, half plus a quarter plus an 8 plus a 16 plus a 32, so on and so on and so on. Using that same kind of square 1 by 1, breaking up in this way, we notice that what we're actually doing is covering up the entire 1 by 1 square, and so that value must be equal to 1 in terms of area. So this shows that it's not just because you have pluses and minuses cancelling out that makes the series converge. Positive series converge too. So the reason it's converging is actually due to the size of the terms and how quickly they get very, very small as you get to very large values of n. And one of the things that we would study in a calculus course at Waseda would be the logic behind this and understand how this actually works for a whole range of convergent and divergent series. Right. Right. At the same time, other series, such as this one, 1 plus a half plus a third plus a quarter plus a fifth, do not converge. This is something which is known as the harmonic series. And there are many others of positives that do not converge. But in this case here, I say the terms are actually getting smaller, but they don't get smaller quick enough to get convergence. And so I say we have to analyze this in detail in a calculus class. But what we're interested in at the moment, though, is, well, how do I actually interpret convergence, right? So how do I actually understand what I mean by these infinite collection of numbers are going to add up to a finite answer, right? So how do I assign a finite value to this? And I said, well, the problem is we can't handle infinity. But what we can do is introduce a limit process that will get us around the problem of infinity, right? Well, what do we understand? Well, we understand finite sums, right? So if we look at parts of this, so like the first term is A1, the second sum is the first 2 terms, the third sum is the first 3 terms, and so on, we can actually calculate all of these because they're all finite, they're all partial sums. Right. And so this gives us a way into actually assigning a value to the infinite series. What we do is we actually analyze what happens to this sequence of numbers as a limit process as n gets large, right? So just like for mouse approaching the cat, we never actually get to infinity, we just get increasingly large. And we ask, well, how does that value change as n gets increasingly large. Right? So we define convergence of infinite series, one of the ways, as a limit process. And we say that an infinite series converges to a value L if the limit, it's that process again we talked about earlier, of the thing we're interested in, that collection of partial sums, as n gets larger and larger and larger, gets closer and closer and closer to this value L, or it approaches this value L. Yeah. So just to show a couple of quick diagrams illustrating this, this is the one on the left. This is the earlier one where we had a half plus a quarter plus an 8 plus 16. And this is the partial sums against the value of n. And here we clearly see these values approaching the value 1. Right? And so as n goes to infinity, we get closer and closer and closer to the value 1. And so that allows us to define convergence of that infinite series. And so we can say the limit of the partial sums is equal to 1. So it allows us to assign a finite value to the infinite series. On the flip side, if we had something like this, this leads to direct problems, because if I look at this series, well, if I start here, and I do 1 minus 1, that's 0, plus 1, which is 1, then minus 1, which is 0. So if I collect terms like this, well, then I would expect the series to be equal to 0. But if I took, say, the first value, and then did minus, and then 1 minus 1 minus 1 this way, then I'd get the answer 1. And that should be a warning sign that something is not working here. Right? And in fact, we can show that convergence is not working just by looking at the sequence of partial sums. Because if we look at the partial sums, we go from 1 to 0 to 1 to 0 and backwards and forwards, it's clear that as n gets larger and larger, these values do not converge to a particular finite value L. And so this is not a convergent infinite series. We cannot assign a value to it. Okay. On an aside, we're quite lucky that see a series like this one are actually closed form. We can actually work out these things analytically. A lot of cases we can't work out the values. But the actual partial sums that we're interested in are just geometric sums, and then we learn at high school how to actually collate a geometric sum and find that it takes this value. And then in particular, if r is less than 1 in magnitude, then taking it to larger and larger powers just makes this smaller and smaller and smaller. And so going out to extremely large values of n just makes this thing effectively vanish. And so we get that in the limit, as n goes to infinity, that the geometric sum becomes a geometric series and limits basically to a over 1 minus r. So this is a collection of series which we can actually work out exactly what the answer is. And so that applies precisely for this case, and it also applies for the mouse case we saw earlier, where the mouse is running backwards and forwards. That is also a geometric series. Okay, so this is one example of where we end up very quickly in a situation where we have an infinity coming into play, and then we use the idea of a limit to get around that problem and establish a result relating to convergence for that process. The flip side of this is now going to be in terms of differential calculus, where instead of looking at going out to infinity and infinitely large values, we're going to look at infinitely small values. Differential calculus, there are lots of different points of view. There's a physical kind of motion point of view, rates of change. There's obviously an analysis point of view. But the thing that we're going to be interested in today, the point of view, will just be in terms of geometry. In which case, then, we're talking about using calculus to find the slopes of different functions. So we'll start by doing the easiest possible case, which is the slope of a straight line. So if I have a straight line y equals mx plus c passing through the points x1, y1, and x2, y2, then I can easily back out what the slope should be. It's basically the difference in y values different x, or rise over run, will give me the slope. But what I'd like to be able to do is to calculate the slope of a general curve, right? Not just one which is a straight line, right? So if I'm given a curve, how do I calculate its slope? Right? Well, we don't know actually how to do it, right? But what we do know is how to calculate the slope of a line, right? So what should we do? Well, let's take the point that we want to know what's the slope of the curve. let's add on a tangent line to the curve, so a line which just touches onto the curve and passes by it. And instead of working out the slope of the curve, we'll work out the slope of the tangent line. We'll define that as being the slope of the curve at that point. But the difficulty with that is, to do that, I have to look at the curve and I have to draw it, right? And as a mathematical process, that's generally flawed, right? What we want to do is a mathematical process that will actually pick that out for us. And so the idea is instead to say, well, let's actually choose some points, say Q1, and then we'll draw a line between Q1 to the point P, and imagine the line going out to plus and minus infinity, and I'll use that as an initial approximation to the tangent line. And then as I bring Q down closer and closer and closer to P, then I expect the tangent line, sorry, the line passing with these 2 points, to actually look more and more like the tangent line. And so we then can introduce a limit process that says in the limit that this number here approaches this one, so this point here approaches this one, then the second line that we get will define as being the tangent line. Okay. Right. So for a general function, y equals f of x, the slope of the second is given by this calculation. So this is just basically y2 minus y1 over x2 minus x1. Right. As I say, we expect to get a better approximation to the tangent line the closer that we bring this point towards this one. Now, in the best of worlds, you could say, well, let's just bring it exactly to that point, and then it will be perfect. But of course we can't do that, right? We can't bring h to 0 and actually bring that point directly on top of that one, right? For 2 reasons. Firstly, this quantity would just become completely meaningless, because this value and this would be 0 and this would be 0, and mathematically 0, 0 doesn't make sense. And, well, geometrically, you'd be then trying to define a line by a single point, right? If you have a single point, then any line going through it would work. So it's a process which is not defined for calculating out the tangent line. So as I said earlier, what we have to do to make it work is to introduce a limit process, right? Where we bring in h closer and closer and closer to 0. So this point gets closer and closer to here, but we never ever reach it. And it's the introduction of that limit process that gets us around this 0 over 0, or this infinitesimally small problem that we would have got otherwise. So again, the limit process here helps out. Well, that limit, as h tends to 0 of this ratio we have at the top here, is what we define as the derivative of the function f at the point x. And although it looks complicated and we use this notation to define the derivative, right, all you have to keep in mind is whatever that's written out as, it's just the slope of a straight line, right? There's nothing special to it. It just says at a given value of x, this is the slope of a tangent line to the curve at that point, right? That's all it says. So just to give a quick example, if my function was x squared, for example, then df dx is that limit. Replace f by, sorry, x by x plus h squared. Cancel out the details, work our way through. Importantly here, I can actually take the h on the base here and cancel out with the numerator because of the fact that h never gets to 0, right? The limit process, h never reaches 0, so it's always some non-negative number, and so therefore I can always divide for it. So that's a perfectly okay calculation. And at the end of it, well, if I look at 2x and h, well, as h goes to 0, this is going to get smaller and smaller, so the bit we'll get left over is 2x. So this defines 2x as being the slope of the curve x squared at any value of x that we're given. Right? So just to kind of verify that, here's a picture that I quickly sketched out showing the curve y equals x squared. And then for some values of x, I calculated out the slope based on the 2x, and I've just drawn them quickly, right? Indicating that it does seem to give us the tangent line at the appropriate point. So it does seem to work as a process. Important to look at that, though, is what I notice is if, well, for values of x which are negative, well, then the slope of this straight line will be a negative value. From the positive side, it will be a positive slope. And when I go through 0, it'll actually have 0 slope. So as I pass through this minimum, I'll get a 0 slope calculation. Okay, now, that process I've just done with the Newton quotients, I could try to continue doing basically for any function we're given, right? But there's going to be problems with that. Well, firstly, because we don't have that amount of time, right? You can't do every single function and work your way through all of the details of all that kind of limit processing. It just takes too long. And secondly, when you're trying to do it for more complicated functions, say, for example, this one, then trying to write this is all the x is replaced by x plus h, expanding them all out, doing the cancellation and taking the limit is just horrible, right? And so what you don't want to do is do all those calculations. What you really want is a set of rules that will actually do it for you. Yeah. And this brings me on to this. So the cat and the mouse have made up here. They're now playing chess. But the basic idea is the following, right? You should think of differential calculus as actually just being a game, right? So 3 of the guys at the back here passed my calculus class. So these guys, this is why they're shuddering at the moment. But you should think about differential calculus as being as a game, because if you learn the rules and you learn how to apply the rules, then all it is practice and getting used to them and getting stronger and stronger and stronger. That's all you have to do, right? So as soon as you know the rules of the game, you can do pretty much all of differential calculus. And that's the important thing, because once you can do differential calculus, you can get the mechanics out of the way and you can focus on the concepts and the problems that you're using it for. And that's much more important. So just to quickly summarize, here's a collection of like the main points of the game. And then very shortly, I'm going to use this rule and this rule. So this is a power rule and this is a chain rule. But as long as you kind of know these rules, that's basically differential calculus. That's all you need to know for differential calculus, right? After that, it's just knowing how to apply those rules well and practicing and doing them and learning how to be strong with them. Okay? But as long as you know what the rules are, then it's just a game. You just plow through the calculation and it will give you an answer. And that answer will always represent the slope of a curve at a particular point. So just to go back to talking about that curve about x squared that we saw earlier, a bit of intuition. Well, if you think about if we have a slope which is going to be positive, and that's positive on an interval, then that seems reasonable to imply that the curve will actually be bending, well, will actually be going upwards. And if the f dx is negative on an interval, then we'll have a negative slope at all the tangent points and suggest that the curve is going down. Right, so here's just a random curve that I've drawn. And so in regions where we have negative slope, the curve is going downwards, positive slope going upwards, upwards and downwards. And notable, there's several points there where we get a 0 slope, particularly a maximum and a minimum value. We get a 0 slope. And one of the most powerful applications of calculus is finding maxima and minima of quantities. And we'll use this in this application very shortly. We do have to be careful of places like this, which is an inflection point, which also has a derivative equal to 0. But it's always easy to distinguish inflection points from maxima and minima because of the fact that, well, in a minima, you go from a negative slope to positive slope, and max, you go from positive slope to negative slope. At a point of inflection, you always keep the same slope, positive to positive or negative to negative, on either side of the point. Okay. So importantly, a maximum or minimum point, you have df dx is equal to 0. Okay. So to finish up, to kind of take this and actually apply this to give it an action, we're going to talk a little bit about Snell's law that you guys have probably come across from your physics or chemistry or biology classes. So what we're going to do is if we assume that a light ray travels from the point A, refracts at a boundary between two medium at some location x, and reaches the point B. And what we'd like to know is, well, what's the path taken by the light ray? Well, Snell's law tells us exactly what it is. If we know what this angle is, and this, well, if we know what this angle is, then we can calculate the other angle using this ratio of sine A over sine B equals a constant. Now, I should be careful here. This is not just any constant. Obviously, if you take sine of A over sine of B for two numbers, that's a constant. What I mean here is that there's a special constant for which this is always true, meaning if I move this point A to somewhere else and I shoot a light ray over to here, and then I find a point over this side where it passes through and call it B, and I look at the sine of that angle over the sine of that angle, it will be exactly the same number. That's what Snell's law tells you. Okay. And what we'd like to do is actually now derive that using calculus. And in particular, we're going to do it by saying, well, suppose I know that I have a light ray that goes from the point A, refracts at some value x, and goes to the value B. Well, what's the path that that light ray actually takes? How do I actually find this location x? How do I know it doesn't go over here or doesn't go over here? How do I find the location x that chooses that value? Right? As a part of this process, we're going to find Snell's law as a solution. Okay, so let's quickly summarize what we know. Speed of light depends on the medium which it travels. We're assuming that both mediums are uniform. So the speed in the upper medium will be constant. We'll call it Cu. The speed in the lower medium, Cl, will also be a constant. The second point we'll take from physics is Fermat's principle of least time, that a light ray will travel between 2 points along a path that minimizes the time taken. And that's the important phrase here for calculus, minimizes. Because if we can write down a function for the time taken of the light ray, then looking where that function is minimized, where it has a zero derivative, we'll basically pick out the value of x. So that's the process we're going to be doing. So physics 1 and physics 2, and finally math 1, if you're looking at lines, points in a plane, well, the shortest distance between them is a straight line. Okay, so firstly, if I apply physics 1, physics 2, and math 1, then if I'm in, say, the upper point over here, and I have a line ray that goes from this point to this point, well, because Fermat's principle of least time says it has to take the shortest distance, shortest time, and it's traveling at its constant speed, and the shortest distance is between straight line, therefore, in each of these mediums, the light ray has to be straight. Right, so we haven't assumed that yet. I drew it in the diagram, but I haven't actually proved it. But those three statements make sure that in the upper medium and the lower medium, the light ray has to be a straight line. Okay. So I said there, in addition to this, we also have that velocity is equal to distance over time, because we're moving at constant speed. So therefore, we can define time as being distance over velocity. Right. So what we want to do is to construct now the time taken for the light ray and then minimize that value, that function. And I say, because we know it travels in a straight line in both the upper and the lower, the calculation for that is straightforward. It's just in terms of Pythagoras. So the time taken from A to B is basically 1 over the speed multiplied by the distance taken by the Pythagoras calculation. And if I can minimize this function, then the value of x that does that will give me basically the exact location where the ray passes through the boundary. Right, so if I calculate out the derivative, and again, the cat and the mouse are here just to remind you that this is just a game, right? If you apply the power rule and the chain rule to this thing, this is what you get. And as long as you just know how to do that and you know how to do it well, then this is a trivial step. Right? And so one of the things that you learn in calculus, probably at high school but also university, is just to do this over and over again so you get stronger at it, so that it doesn't get in the rest of the way of the calculation. Right? So if I want to find that special location x where that light ray changes direction, refracts at the boundary, then I need to find out where this thing is equal to 0. Right? So therefore, I need to find it being a possible minimum when that quantity is equal to 0, or in other words, when this bit equals this bit. Now, straight off, I know that can't be a maximum, because if it was a maximum, I could actually draw a line not going like straight and then bending, but I could go off out to extremely large values and come back again. So this clearly can't be a maximum, so therefore we expect it to be the minimum. Right? But we do have to be slightly careful with the calculation. All right, so if I can find the value of x from this thing, well, then I'd know exactly where the light ray bends as it hits the boundary. But that is quite nasty, and I wouldn't want to have to go through that and calculate out the value. However, if we actually look at this for a little while and think about our trigonometry, well, this is just length of one side of the upper triangle and the length of the lower side of the triangle, and this is just the length of the hypotenuse. So actually, what those two quantities actually represent are just sine A and sine B. Right? So although I don't really want to work out the value of x that actually does this exactly, I could work it out based on sine A and sine B. What this actually tells me is that sine A over sine B is a constant, irrespective of the values that I choose for the location A and the location B. And in particular, it tells me exactly what that constant is. It's the ratio of the velocity in the upper medium over the velocity in the lower medium, which is precisely Snell's law. So Snell's law here drops out of this calculation by looking at minimization of the time taken. Right. 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 So now just to quickly talk about why it's the minimum. Well, if I look at x equals 0, so that left boundary, well then dt dx is negative. And we've talked about this before. Dt dx being negative means negative slope. So therefore the function's going down. And for large values of x, dt dx is positive, which suggests that the function's going up. Okay. So therefore, we get this unique value of x where dt dx is going to be minimum. We go down here, and then we go up here, and there's a minimum value here, right? That makes sense? Yeah. Right. That's not actually true. Right? That's actually a flawed argument. Right. The guys who are taking calculus with me are smiling because they know why it's flawed. So why is that a flawed argument? Why doesn't that justify me having dt dx equal to 0 at a unique value somewhere in the calculator? I go down here, I go up here, so therefore dt dx should be equal to 0, a unique value at the base. Why is that flawed? Again, you guys you weren't expecting questions today, right? So why isn't that clear at the moment, right? Why is there a problem with that statement, right? Let me put a picture up, right? So this is what we're assuming, right? We're going down, we go for the minimum, we go back up again. So we know we're going down here, going up here, so we must connect through here and have a minimum here. Do you guys see the flaw in the statement so far? No? All right. Well, nothing says there has to be a unique minimum at the moment, right? All I've said is that this side we have to go down, that side we have to go up. Anything else can happen in between, right? Right? Nothing we've actually done in the calculation has said anything at all for what actually happens. There could be multiple minima, multiple maxima. Of course there isn't. There's only one value, and that's the value that gives Snell's law. But nothing in the mathematics that we've done yet has actually shown that to be true. Okay, and so the last question I'm going to leave you guys with is basically, well, how would you actually check? What would you do to work out whether you do have a single minimum or is there something else going on? Any questions? Any suggestions? No one willing to be brave? Okay. So the one thing that you could do is to say, well, over here it's negative, right? And over here it's positive. And then ask myself, well, does that actually change, right? Am I always going from negative values of slope to positive values of slope? In other words, is the slope increasing as x changes? And so what we can do then is instead is to actually say, well, what does the derivative or the rate of change of the slope of the derivative do as the variable changes? We can look at what we call the second derivative. And so the second derivative would tell me then whether this thing is always going from negative to positive or whether there are variations. And in actual fact, if you look at the original form, if you do calculate another derivative, you can in fact show that that thing is always positive. So that the slope function is actually always increasing. And so you always do go from negative through 0 to positive. So in actual fact, this is the correct shape, but what we said up here wasn't officially true, right? We have to kind of do a little bit more work to prove that that's the case. So on that note, I will finish. And if anybody has any questions or anything else they want to talk about, please feel free to ask questions. Okay, thank you very much.